let's talk about chemical equilibrium. This will be chapter 15 in our textbook. When we think about equilibrium, we can go back to those calculus problems that you hated dealing with, where you have water coming into a vessel and water going out of a vessel. And either, one of those two values was higher than the other in terms of rates, and eventually either the tank would overflow or it would empty, or it would just get to fill whatever the question might ask, right? In chemical equilibrium, though, we're looking at a state at which the amount going in and the amount going out are the same. And as a result, if this were the case of a water tank, if we're putting water in at 5 liters per minute and water is draining out at 5 liters per minute, if those rates are identical, nothing changes. The water level doesn't change. And while this is a math or physics example, overall speaking, because the rates of water going in and water going out were the same, the system is overall neutral. Nothing's changing with this system. And we're going to see that this is the same case for chemicals in chemical reactions. The same occurs when reaction rates are equal. And specifically here, we're looking at forward and reverse reactions. If we were to take a particular reaction, see that most reactions in chemistry are equilibrium reactions, meaning it's possible to go backwards and forwards. Technically speaking, all reactions are reversible, right? We saw in the last chapter that we just have a bigger energy barrier to overcome if we had an exothermic reaction to go backwards, or an easier barrier if it's endothermic. But in either case, we can get reactions to happen in reverse if we really, really tried to. Some reactions, though, are happy to go at forward and reverse just at neutral conditions. And so we have a special arrow for this. We call it equilibrium arrow. And this is to denote that the process is happening in the forward and reverse directions simultaneously. Some reactions we're okay to use a one-directional arrow because it's very difficult to make the system go backwards. For example, if we take a piece of paper and burn it, that's a chemical reaction, right? We're producing CO2, water, and some ash. But if we take CO2, water, and ash, it's very, very unlikely we will get a piece of paper out again in reverse, right? So some reactions were pretty safe to go ahead and put a single direction arrow, to like a combustion reaction. But we're going to see that many reactions are perhaps better suited with an equilibrium arrow instead. This reaction will be using extensively as a sample sample reaction throughout this chapter. And so it's a very industrially important one. It produces most of the fertilizer that keeps our population alive. It's a very important way to fix nitrogen. But suffice it to say that if we take a look at the rates of this reaction, consider the forward reaction, which is hydrogen and nitrogen coming together. Technically speaking, we should probably balance this equation. All these are gases, right? And then the ammonia will produce 2 moles of that as we go through this reaction. If we take a look at the rate of the forward reaction, and if we assume it's going to be based on the concentrations of our reactants, again, we're going to kind of make the incorrect estimation that the rate is dependent on what's this is a tetramolecular reaction here, but suffice it to say that we're really only looking at it doesn't matter that this is not the correct rate law for this. We can still kind of deal with the rate respective to all these reactants. And so with that, we would say, okay, well, the rate of the forward reaction, we'll use its F to indicate forward. Again, if this were the overall reaction, if this were elementary, we could say that as our rate law. For the second, of course, we're looking at the ammonia, so that would be KNH3 squared. And let's just say this is R for the reverse reaction. So K sub R would be our rate constant here. At equilibrium, which is the state at which nothing changes, that's when our in rate and out rate are the same for the water tank. And we're going to see that for a chemical reaction, when the rates are equal, equilibrium is established. That means at equilibrium that these two are equal to each other. And if you remember back in kinetics, we talked about this idea. We use K1 and K minus 1 when we're talking about slow second step reactions. So that, again, kind of took into the idea that our first step was an equilibrium reaction, something that's reversible. But once the equilibrium established, the rates are identical to each other. The rate of the forward reaction and the reverse reaction are equal. Just like with the water tank, the water coming in and the water going out are equal rates. And as a result, nothing changes. That's equilibrium. And so, if those rates are equal to each other, we can set these terms equal to each other. And we can kind of group stuff. We can say, okay, well, if we move our rate constants to one side, and we move everything else to the other side, we can end up with what's called an equilibrium expression. That's this part on the right here. And if we consider these K's, they're just both constants, right? And if they're both constants, we can just combine them to make a new constant. And we can instead get rid of these K's and combine it with a new one, which we'll call Kc, which will be an equilibrium constant. So we're going to combine the two rate constants into a new constant called Kc, which is an equilibrium constant. And since we know that the K's were constant, right, at a given temperature, and we know that those rates were equal, we now have a new constant here called the equilibrium constant, Kc. In this particular example, it's related to the concentrations. We'll see we'll have another K for pressure. But suffice it to say, if we take a look at what we've established here, this equilibrium expression, we'll see that this is really our products over our reactants, raised to their individual powers according to our chemical equation. We saw that for this equation, we had 3H2 and N2 turns into 2 NH3s. And notice on the top we have NH3 squared raised to its power, the products of this reaction. And on the bottom, we have the reactants. We have the hydrogen raised to the power, third power because it had a coefficient of 3, and then we have the nitrogen there. And so, this is an extremely valuable term because we know then, once we can establish the concentrations at equilibrium, we'll find out the value of this constant. And once we know the constant, we can apply it to new situations. And that's something we'll explore in later videos. But with this video, I'd like to wrap up by kind of just summarizing the definition of what equilibrium is. So equilibrium is where we have no net change in concentration of any of our components. So no concentration is changing. Just like in the water tank, the water level doesn't change. So our amounts of hydrogen, nitrogen, and ammonia stay the same. Of course, it's not to say that all the same molecules of hydrogen are there over time. They are reacting, but the ammonia is breaking down at the same time, at the same rate. So things are becoming ammonia. Ammonia is becoming the hydrogen and nitrogen again. And so the forward and reverse rates are equal. And finally, a very important consideration is that the system must be closed for equilibrium to occur. Meaning we can't have our container open to the atmosphere. If we're looking at concentrations of ammonia, hydrogen, and nitrogen, if we just open that up, things are going to fly out and new things are going to come in. And so we're not going to be able to talk about the equilibrium then, because our reactants and products have gone away. They have vanished. So the system must be a closed system for equilibrium to occur. And so, again here, we see no net change in concentrations or pressures if we're looking at gases specifically, partial pressures, that is. This occurs because the forward and reaction rates are equal after equilibrium is established, and we must always consider that equilibrium can only exist in a closed system. We've seen it before, right? When we talked about vapor pressure. In a closed system, if you put a liquid in that's volatile, some proportion of those molecules will come out as a gas. And that's only going to be true in a closed system, because if we open that system, those gas particles just go away. And that's why water will completely evaporate over time. However, if we have a water bottle that's sealed, a closed system, that water will never evaporate fully. Like, you'll still have the same proportion of liquid water and gaseous water on top of it. But if you dump that water out onto a plate or something and just leave it out, that's no longer a closed system. The water evaporates and eventually it's gone. And so that's not an equilibrium. But in the water bottle is an equilibrium. And so this concludes our introduction to what equilibrium is. In our next video, we'll take a look at the constants of equilibrium and how to use them.